All right. So what questions do we have today? So I'll just I will reserve questions that I haven't answered on video before, unless there's no other questions, and I can redo a question that I've answered on video before, just to maximize the number of questions for which we have video solutions to, which seems to make sense. But what questions do you guys have that haven't been solved on video before?
Is it okay if we do number 4?
Number 4 from
Chapter 15.
Let's see.
I could draw it in the extensive form, but I don't know what to do after with the equations.
So exercise 3, chapter 14. Wait. This is just the this is the Stackelberg. This is the same Stackelberg that we had in the lecture notes. So the total the demand in the market is P equals 12 minus Q1 minus Q2. There's 2 firms. Or am I looking at? Oh, this is chapter 14. I'm sorry. It said chapter 13, right? Number 4, chapter 13. Is that the reference?
Yeah, it's asking for chapter 14,
Oh,
exercise.
chapter 14.
Yeah,
Exercise 4.
exercise. So it says calculate and report the subgame perfect Nash equilibrium of the game described in exercise 3 in chapter 14.
Oh, sorry, exercise 3. Sorry, exercise 4 is just the Stackelberg game. So, question. So let me go to the whiteboard. So this is.
Here's what I found.
So this is chapter 15. Chapter 15. Number 4. And this is finding the subgame perfect Nash equilibria of chapter what was this chapter? Chapter 14, question 3. All right. So consider the following game. Player 1 selects a number X, which must be greater than or equal to 0. Player 2 observes X, then simultaneously and independently selects a number. Oh, right. This is, didn't we do this one? We did this one.
I think we did 9, which is kind of similar.
Okay, so this is, yeah, just let me look real quick. Yeah, it must look real similar. All right, so
like x over like x to the third or something like that.
right. So player 1 selects number X. And then player 2 observes it, and then they simultaneously and independently pick.
So with the simultaneous, then it's going to be dotted lines, right?
Correct.
Okay.
All right, and then the payoffs are I swear we solved this one. I made mistakes on the derivation. Like I forgot to put the one of the numbers in there, either x times y1 the solution ends up being y1 or x equals y1. So whatever player one picked in the beginning, he picks the same number at the end. Man, this seems really hauntingly familiar.
Is x 1 over 3?
This one here. Y2 squared. Okay. So we have to so in the second period, like when player 1 and 2 both simultaneously move, they both take x as already given, right? So we solve the games from back to front. This is like the backward induction. So we player 1 can't revise the choice of x once she's making the choice in that second period where she's picking y1 and player 2 is picking y2. So x is already given, so we treat it as if it's a constant. And so player 1's derivative with respect to, sorry, this is respect to y1, and he's treating, he's making a guess of what is y2, and he already knows what x1 is. So this derivative is equal to his guess of y2 plus x, which he already knows because he picked it in the first period, minus 2y1, and then the minus x to the third divided by 3 falls out because it's just a constant. All right. And the second derivative of this thing is just -2, which is negative, so it's concave problem. And we let that be y1 star. So here we're going to have that y1 star is equal to 1/2 times y2 bar plus x. Okay. So that's the best response function of player 1 once x has already been chosen and simultaneously forms a belief about the action of player 2. And player 2's best response function is, so this requires that we use the chain rule. I won't make you guys use the chain rule on your on the final, but you have to take the derivative of the function on the inside of the parentheses. So we do -2 times y1 minus y2 to the first power, and then we have to take and that's a y1 bar. It's a belief about player 1. And then we have to take the derivative on the inside of the parentheses, which is just -1. Okay. And so that equals 2y1 bar minus 2y2 star equals 0. And so y2 star equals y1 bar. Okay, so player 2 just wants to make a guess about what player 1 does and then imitate it. And that should be clear from the utility function because inside the parentheses is y1 minus y2, and we're going to square that and take the negative. So the best that could possibly happen is that player 2 gets a payoff of 0, a utility of 0, when the two numbers equal each other. Otherwise, the further apart they are, the more negative they're going to be. Okay? So these are the best response functions. And so in equilibrium, going back to, so in equilibrium of this subgame, remember it's a subgame perfect Nash equilibrium, so both players have to be playing equilibrium in every subgame. So the subgame where they move simultaneously, we have to have y1 star equals 1/2 times y2 bar, and we know that that's going to be equal to the same thing as y1 star. So we make the substitution of player 2's best response function into player 1's. Okay, and so I can subtract 1/2 y star from both sides, which means I'm just going to have 1/2 y1 star on this side is equal to 1/2 x on this side. So clearly y1 star equals, we already know it's equal to y2 star equals x. We definitely solved this problem, right?
Yeah, I just looked at 9 and it's the same except for it just asks for player 2 observes X in 9. It's just the opposite, so it's okay if we skip it.
Oh, okay. Well, I mean, so now we're almost done. So
Okay.
might as well finish it. No, that's what I see. But yeah, it's like these numbers look too familiar.
Yeah, I just didn't recognize that it was asking for Stackelberg when it
I
was
see.
asking for the
But
Nash equilibrium.
okay, but no problem. This is going better than the first time. So now in at the beginning, player one knows how the game is going to resolve. Like player one knows that whatever she picks as X is also in the sub game going to be the same value as Y1 star and Y2 star. And so she's going to be able to substitute those values of Y1 star and Y2 star into her utility function before doing the optimization. So she knows in SPNE, she knows that her utility is going to equal x squared, because there's the first part of her utility function is y1 times y2, but both of those values are going to equal x, and then another x squared, x plus y1, which she knows is going to be x also, and this is going to be minus x squared, and then minus x to the third over 3. Okay, which is just equal to x squared minus x to the third over 3. All right, she knows that's going to be true, that her choice of x is then going to dictate what later happens to y1 and y2. And so now she takes the derivative of this utility function with respect to x, and she gets 2x minus x squared. And the second derivative of that is going to be -2. No, it's going to be, sorry, the second derivative of this is going to be 2 minus 2x, which as long as x is greater than 0 is going to be a negative number, and x has to be greater than or equal to 0 by assumption. So this function is concave on the domain that we're allowed to pursue. So we can set that equal to 0, and then that's going to be our x star. I'm not going to put a star in there yet because there's a squared, and it's going to look a little messy. So we know,
Professor, it's
yeah.
supposed to be x to the 1/3 power.
Say again?
It's supposed to be x to the 1/3 power.
What is supposed to be?
X to the 1/3 power for the original equation, not x3/3.
Oh, wait. It's the utility function, that's x to the third divided by 3. So this right here is okay. It's x to the third over 3 it's 1/3 times x to the third. That's what they gave us as the utility function. So we're good here, and then we're good here, and then when we take the derivative of that second term, it's the 3 goes out in front, and so the 3 on the bottom drops out, and so it's just negative x squared. So this should be good.
Okay, sorry.
No worries. And so we know that x times 2 minus x equals 0. We might as well throw our stars in there now, since the exponents are gone. Okay, and so we know that either x star equals 0 or x star equals 2. Those are the two solutions to that equation. we also know that if x equals 0, utility of player 1 is 0. So we can see that by just substituting into that top function up there. 0 squared minus 0 to the third over 3 is 0. But if we plug a 2 in there, we get 2. So we have x squared is 4, and then minus x to the third, which is 8 over 3. 4 minus 8 over 3 is a positive number. And so we know the solution that we want is this one. And the reason we're getting two solutions there is the fact that at x equals 0, this is not a concave problem anymore. That the slope, the second derivative is equal to 0 when x equals 0. So on the rest of the domain, we would get a unique solution, but here we have two solutions because so we have to check that the x equals 0 isn't a better solution, but it's not, it's worse. And so the SPNE is that x equals 2, y1 equals 2, and y2 equals 2. So all the values for all three choice variables are 2 in the subgame perfect Nash equilibrium. All right. Anyone have any questions about that problem? The math is a little bit more challenging. You have to use the chain rule. We have two solutions, so it's a little bit more advanced than what we've done in class or what I put on the final exam. But the way that you go about solving it is definitely something eligible to be on there, in the sense that you have to understand that player 1 and player 2 moving second, we have to solve that part of the game first, and we're going to apply a backward induction. So we take the choice of x as given, solve for x1 or y1 and y2 simultaneously in the subgame, find that equilibrium, and now plug that equilibrium back into the original game, and then maximize the utility from player 1's perspective, knowing what's going to happen in stage 2. That's the key to this question. The math is a little bit more tricky than what I'm going to have on the final, because I'm not expecting you to remember the chain rule. Questions about this one?
Professor, I have a question about different problem.
Yeah.
The one you did in video chapter 15, the second video, when there's a 8 by 4 table.
I don't remember it. What number is it?
It's the one you went over in your lecture, the video lecture. So we ended up with 6 solutions, but we only pick only 2 of them.
Oh, okay. So we found 6 Nash equilibria, but only 2 subgame perfect Nash equilibria that were pure strategies. Is that right?
Yeah, that's the one.
Okay.
So I still cannot figure out why it's only 2. I know why it's we don't pick up 2 of the other ones, but I'm not sure about the other 2. I don't know how to.
You'd have to remind me of what the game is. I don't remember the game at all. So how does it? So presumably it starts off with player 1. And what choices does what choices does player 1 make?
Let me see if I can just make a screenshot.
Well, yeah, I have the video lectures here too. Let's see if is it in part 1 or part 2?
Part 2.
I think it's the
and
question.
is it okay, I see
towards the end.
Yeah, I got it. So we have player 1 chooses A or B, and this is from chapter 15, video lecture 2.
It make more sense. Okay, so you have something. Okay.
Player. Yeah.
And this would be equivalent even if the game B, even if B was out, a strategy out, and there was no subgame after, it was just a payoff of 5-3, it'd be the same thing. Because of the knowledge of rationality,
Sorry.
Like, that's my voice. I'm like, that guy knows what he's talking about. Who is that guy?
It's more towards the end, like it's like 10 minutes before the video finishes, when we have already the table 8x4 and we have 8 solutions circled, but we only pick up 2 of those.
Right. So let's see. So let's, oh, 1 sec. What happened to? There we go. 0, 0, 2, 6, 6, 2, 4, 4, 5, 3, 4, 4, 2, 2, 6, 1. And we found that in the bottom subgame, there is a unique Nash equilibrium. So in this, so I won't solve these since they're solved in the video, but we found that this Nash equilibrium here is YZ. No, can't be. This is EY, sorry. I think someone just chatted. I can't see all this stuff simultaneously on my screen, but I think I saw a message. Someone asked if I'll post the video. I will post the video, provided that the video saves and everything. So it's like my plan is to post this video, and I haven't had any problems doing that before, but you never know with technology. So my plan is to post this video after we're finished, for sure. So the Nash equilibrium in the bottom is EY. The Nash equilibrium in the top is there's 2 pure strategy equilibria. So one of them is DW and the other one is CX. So CX and DW. Okay. So yeah. So in the subgame perfect Nash equilibrium, we know that in the top we must either play CX or DW, and in the bottom we must play EY. There's also a mix. There's also a mix up here, but let's. There's also a mix up there in the top, but let's forget about that for now. So when player 1 makes the choice of choose of A or B at the first node, he has to, in an equilibrium, he'll know which equilibria all the subgames are played in as well. So he'll know whether the top subgame is played in the CX equilibrium or the DW equilibrium. If it's played in the CX equilibrium, player 1's payoff is going to be 6, whereas in the EY equilibrium, player 1's payoff is 3. So if CX NE in top subgame, then player 1 chooses A because A gives a better payoff than picking B. So SPNE is A for player 1 in the top, and C, I'm sorry, he picks A at the first node, picks C in the top, and picks in the bottom, he always has to pick E because it has to be an equilibrium in every subgame. Whereas player 2, we've agreed that it's the CX equilibrium in the top, so must be playing X in the top, and in the bottom always has to play Y. Okay, so that's subgame. So that's one subgame perfect Nash equilibrium. Player 1 believes that the top subgame will be played CX, so he plays A because the payoff is better than playing B. and he has to be correct in his belief, because if he was incorrect in his belief and the top top subgame we played in a different equilibrium, then player one would want to revise his strategy so it can't be an equilibrium. Okay, so the top one subgame perfect Nash equilibrium is this one, and then and another one is if the top subgame is played in DW. If the top is played in DW, player one gets a payoff of 2, but by going B, he still gets a payoff of 5. So if the top is played in DW, player one chooses B, and then the SPNE in that case is going to be player one picking B, and then in the top subgame they're playing DW, so player one is playing D up top, and then player one always plays E in any subgame perfect Nash equilibrium in the bottom, and player two must be playing W in the top and always must play Y in the bottom. So that's another subgame perfect Nash equilibrium. So we found these two. So these two pure strategies are subgame perfect because they implement an equilibrium of every subgame. So all 3 subgames, the 2 yellow ones plus the full game, all of them are played in equilibrium, and every player is doing the best they can, in the full game. So yeah. And there's also one more subgame perfect Nash equilibrium, where the top subgame is played in the mixed strategy equilibrium. I showed that in the video lecture. So that one has a payoff to player one, an expected payoff of, I'm looking through my video, I'm not seeing I'm looking for the math. There we go. Player one gets a expected payoff of 3. So a third SPNE is top subgame played the mixed strategy equilibrium, and that mixed strategy equilibrium has player two choosing W half the time. So we can write it as player two has sigma 2 equal 1/2, 1/2. And if player two is playing 1/2, 1/2 between Y and Z, then player one, the expected payoff of player one equals 3. So choose B. So player one's going to pick B, and at the initial node, because she knows that if she goes B, she gets a payoff of 5. If she goes A, and they play in the mixed strategy equilibrium of the top subgame, that her expected payoff is 3. So B is the better choice. But then the top subgame has to be played in the mixed strategy equilibrium, and the bottom one still must be played with her choosing E. Okay, so yeah, and then I mean that's all spelled out in the book. So in order to write that subgame perfect Nash equilibrium, so since player one has 8 strategies available, we'd have to then list all 8 of those strategies so that I know what order to put that stuff in. But the important thing is that she's in the mixed strategy equilibrium. Both players are playing 1/2, 1/2. So it's basically choose B for sure, and then choose E. But if I had picked A, pick 50-50. That's player one strategy in the third subgame perfect equilibrium. So there's 3 subgame perfect Nash equilibria in this game. 2 of them are pure strategies. So all of the ones that we circled are Nash equilibria in the matrix form, but only only two of them are subgame perfect. So someone just posted, why is CX in equilibrium in the top, but not FZ in the bottom? So the FZ. So if player one is picking F in the bottom subgame, then if player one picks F, player two won't choose Z, she would pick Y. Because if player one is choosing F in the bottom subgame, so this is player one here. If player one is choosing F, player two's payoff choices are by choosing Y, she gets 4, and by choosing Z, she gets 1. So player two, in response to player one picking F, would want to play Y and not Z. But if player two picks Y, player one's better off choosing E instead of F because the payoff is bigger. So if you put this subgame here, if you put that subgame into a matrix, it's a 2x2 matrix, you'll find that YE, let's make sure I got that right. Yes, you'll find that YE is the unique Nash equilibrium of this subgame. But in the top subgame, there are two Nash equilibria, two pure strategy equilibria. This one, CX, and this one, DW, are both equilibria. If player two plays W, player one's payoff is maximized by picking D. And if player one picks D, player two's payoff is maximized by picking W. So that's an equilibrium. And similarly for the CX. If player one picks C, player two should pick X because 2 is bigger than 0. But if player two picks X, then indeed player one should pick C. So those are both equilibria. Does that answer the question?
Yes, thank you.
Cool. And so, okay, cool. All right, other questions? Let's move to a new whiteboard.
Is it okay if we go over the answers for 11 because there's no key? I think I have them all right, but I'm not sure.
This is 11, chapter 15.
15, yeah.
Let me see. How many proper subgames? I'm never going to ask you that, by the way. Solve the game by backward induction. I will ask that. Find the set of strategies that survive iterated conditional dominance. I haven't talked about conditional dominance. You don't have to worry about that question. Compare the path through the tree that results from the strategy you found in part B with the paths that are yeah. So don't worry about C and D because we didn't discuss conditional dominance.
Okay.
Yeah.
I took test anyway. I don't know if it's right.
Can you say it again?
I took test anyway. I don't know.
Yeah. I'm not. Don't.
Okay.
It's not a. It's not a.
Yeah,
it's not a subject I'm teaching. So yeah, don't worry about it. This game has every player's choice is unique. Every best response is unique from what it seems like because every payoff is unique. So this game has a unique equilibrium. So in games of perfect information, if there's no ties, they're super easy to solve by backward induction. It always reduces to a unique subgame perfect Nash equilibrium. But if there's ever a case where one of the players faces a choice where whichever way she goes, it's a tie, that can open up a lot more equilibrium. But that doesn't seem to be the case in this one. This one has a unique equilibrium. All right, yeah, but don't worry about C and D. Those I'm not talking about conditional about conditional dominance here. So
Would the whole game be considered a subgame here?
yes,
So
yeah.
would it be 8 subgames?
1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. I'm seeing 7.
Okay.
Yeah. So each of the 4 spots that player 1 moves is a sub game, and then player 2, each of the spots that she moves is a sub game. So now we're up to 4, and then, or sorry, now we're up to 1, 2, 3, 4, 5, 6, and then the whole game is a sub game. Again, yeah, I'm not ever going to ask you guys what, like, how many sub games is. That's more of a definitional question. What I tend not to answer. My questions are always more conceptual questions as opposed to definitional.
So
Like you have to know what sub games are to be able to find sub game perfect equilibrium, but I don't have to. I'm never going to ask you how many sub games there are.
So here would it be H, J, K, M, D, E, and B?
Well, we can might as well write it down. A, B, C, D, E, F. Those are all player 1. No information. No dash lines. J, K, L, M, N, and payoffs 3, 4, 4, 3, 1, 2, 5, 7, 6, 5, 2, 8, 9, 1. One thing to notice about this game is how big the strategy space is for player 1. That's something, or for player 1 in particular. So player 2 has 4 strategies. Player 1 has 2 to the 5th strategies. So 32 strategies. So if you were going to put this game into the strategic form, it would be 32 by 4 strategic form, matrix form. So that's a big one. And so that also means that there might be a whole lot of Nash equilibria in that really big matrix. Again, so it's the size of the strategy space. You have to pick one action at every information set. Player 1 has 5 information sets, so her strategy has 5 actions. Now a strategy has 5 letters in it for player 1, and now we have to think of all the different combinations, and that's going to equal the product of the individual action spaces. And so she say each of them is 5, so it's going to be 2 times 2 times 2 times 2 times 2, 2 to the 5th. So anyway, so representing that in the strategic form is going to produce a whole lot of Nash equilibria that aren't subgame perfect. It wasn't the question didn't ask to put that into the strategic form, but it's useful to think about. And now for the subgame perfect, so player 1 is going to pick H here, J here, K here, M here, and those are unique. Given player 1's choices, player 2 is going to pick D here because she knows if she picks C, player 1 will pick H. If she picks D, player 1 will pick J, and player 2's payoff is bigger by picking D. And then at the other information set for player 2, she's going to pick E because K results in a better payoff for her than M does. And now player 1 knows she's going to get 5 by playing A, and she's going to get 6 by playing B, so she plays B. And so the SPNE is for player 1 strategy to be B, H, J, K, M, and player 2 strategy DE. That's the unique subgame perfect Nash equilibrium of this game. But just remember, this is only one strategy for player 1 of the 32 strategies that player 1 has available. So there probably is a ton of Nash equilibria in this game that aren't subgame perfect. All right. That's what you got, Anita?
Yeah, I got this.
All right, cool.
So this would be the answer if you specifically only ask for backward induction for SPNE.
Yeah, that's all I'm ever going to. I'm never basically for chapter 15. I'm going to ask you guys for subgame perfect Nash equilibria. That's the name of the game. And so you find subgame perfect Nash equilibria by backward induction in games of perfect information. I mean, we know exactly where we are at each point in the game. So those are easy. Games that have multiple equilibria games that have like the last game that we looked at, that one could be solved by backward induction in the bottom. So the bottom subgame, the last game on the last page, the bottom subgame was unique, and so we know uniquely what's going to happen in the bottom. But the top had 2 pure strategy equilibria and 1 mixed strategy equilibria, and so that's going to depend earlier in the game. It's going to affect, which of those equilibria are played is going to affect what the action is early in the game. So that starts to create a whole lot more potentials for subgame perfect equilibria. But yeah, chapter 15, the only questions I'm going to ask you related to chapter 15 are to identify subgame perfect Nash equilibria, and be able to put extensive form games into the strategic form and find those Nash equilibria of the full game and do a comparison of the two.
Professor, can you go on over all chapters and approximately what questions from each you're gonna ask, like you did right now from chapter 15? Can you go like chapter 1, you're gonna ask to transform to extensive form, chapter 2, you're gonna ask to transform to strategic form, and so on?
So the final should be roughly equal distribution by time that we spent on material. So the longer we spend on something, the more likely there'll be more questions related to that. It'll be slightly more heavily weighted on chapter 15 because we haven't had a quiz on that. So there would be like, throw an extra question on top of its proportion for the course, but not like exorbitantly so. And then really the thing is, like a lot of the stuff earlier in the course was used to build to the stuff later in the course. So the final is really going to focus on finding, you have to be able to translate an extensive form. You have to be able to translate a description of a game into the extensive form. But is that a chapter 2 question or is that a 15 question, right? Because that you can find that in chapter 2, but you can also find it in chapter 15, where I think anyway, there's some questions in chapter 15 that are saying like, okay, put this game into the extensive form and now do this, that, and the other. So anyway, so being able to take a description, put it into the branches, into the extensive form, being able to take the extensive form and putting it into the matrix form. Like, is that a chapter 3 question? Yes, but it's also a chapter 15 question, because if you're going to look at this game that we have on the screen now, question number 11, if you're going to find the subgame perfect Nash equilibria and compare it to the set of all Nash equilibria, you have to be able to put that into the strategic form, right? So it's both a chapter 3 question and a chapter 15 question. So basically, like, all the chapter 2 questions and all the chapter 3 questions could be like standalone questions, but they could also be part of a chapter 15 question. You have to be able to take this description, put it into the game, into the tree, then put that into the matrix, then find all the Nash equilibria, and now do backward reduction on it. So yeah, it's hard to say, like a breakdown of like how many questions from each chapter, because so much of the earlier chapters I'm using in the later chapters. So it's hard to say what chapter the question came from. But yeah, stuff you have to know for sure is putting descriptions into trees, putting trees into matrices, some of the earlier stuff before we got to rationalizability. So, you know, what is the best response set? What's the best response to a particular belief? What's the notation for beliefs, like your thetas and your theta minus I and your sigma I? I'll have a couple questions that are like that. So let's say chapter 4, 5, 6, but they're not an emphasis. Those chapters were more trying to give you the building blocks that you're able to do chapters 7, 8, 9, and 11 and 15. Like so that the chapters 4, 5, and 6 are mostly about building apparatus, mostly about building notation, so that we can get to the good stuff in chapters. I guess that was chapter 4 to 7. I think chapter 4 to 7 are mostly building blocks to get to chapter 8, which is rationalizability. No, 7. I'm sorry. Now I remember what it is. 4, 5, 6 are building blocks. 7 is rationalizability on matrices. 8 is rationalizability on non-matrix games. And then 9 is Nash equilibria. 11 is mixed strategy Nash equilibria, and then 15 is subgame perfect Nash equilibria. So really, like, most of the course is about rationalizability, Nash equilibrium, and subgame perfect Nash equilibrium. Chapters 2, 3, 4, 5, 6 are mostly there to help us get to that point where we can start talking about how people play games. But I will probably throw a couple questions in there, like, hey, if theta minus 1, here's a matrix A, B, C, X, Y, Z. If theta minus 2 equals 1/2, 1/4, 1/4, what is the best response of player 1 to given theta, best response of player 2 of theta minus 2. So I could ask something like that. I could also say, what is B1, for example. So B1 is the set of all best responses to all possible beliefs. We know that in a 2-player finite game, that B1 and UD1 are the same sets, right? So B1, there's always an equivalence between those two concepts. So yeah, I'd say out of all the early stuff, know how to translate descriptions into trees into matrices. You're definitely going to have to be able to do that. Also know what is theta or sigma I, what is theta minus I, what is BRI, what is BI, what is UDI. So I think that's pretty much all the notation. So if I throw just BRI and a theta minus I, I'll expect that you know what those mean. And maybe there would be, if there's 20 questions, that's probably a good guess. 20 questions on the final. There'll be a couple questions that are that ask, basically are just tests of your knowledge of that, what BRI is, but very few. So there's not going to be a lot of questions of that nature. They're going to be more about, what's the equilibrium of this game? What is it? Is it subgame perfect? All that kind of stuff. But yeah, that's the nice thing about a course like this is like in chapter 15, you can like with the exception of chapters 4 through 8, chapter 15 uses every single chapter that we went through in the course, right? It uses chapter 2 a lot, it uses chapter 3 a lot, it uses chapter 9 a lot, it uses chapter 11 a lot. So it's like it's building on all that other stuff. So a chapter 15 question is really using 2/3 of the chapters of the book, if not more, to this point. So if you understand the chapter 15 questions, there's really no reason to like spend a lot of time reviewing chapter 2, 3, etc. Okay. But But yeah,
And from chapter 8, what kind of questions should we expect? Are you gonna put some social unrest kind of problems, or?
Yeah, I mean, it'll be, just understanding the concept of rationalizability. It could be, I mean, the midterm would be the best bet of the types of questions I could ask. So it could be, a game that we studied in chapter 8 directly. It could be from chapter 8, end of chapter question, or it could be something that's similar to something we did in the lecture or in the end of chapter question, but just like a slight twist on it. But it'll be one of those things. So chapter 8, and chapter 8 questions are typically among the tougher ones in the course, for sure. I mean, I think it's the hardest chapter in the course. So I mean, yeah, it could end up being, more challenging than some of the other ones. The level of difficulty overall on the final will be a little easier than the midterm, because the midterm was focused on some of the tougher chapters of the course, whereas the final will be more comprehensive. So I mean, to the extent that you think taking a paragraph description and putting it into the extensive form, like that wasn't tested on the midterm, but it will be tested here. Being able to take that game and number 11 above and put it into a matrix. Now that probably wouldn't do that because it's a 32x4 matrix, but being able to translate extensive form to strategic form, like I view that as an easy question. So if you agree that that's an easy question, that question should be pretty fast and help build your points in the final. You didn't have questions like that in the midterm, or the question below. If theta minus 2 is equal to 1/2, 1/4, 1/4, what is the best response of player 2? That's just, okay, that's the belief of player 2 about player 1. Player 2 thinks player 1 is doing this. Given that player 1, he believes player 1 is doing that, you can calculate the utility of X, the utility of Y, the utility of Z, and expectation. Just weight each of those by the probabilities, and then pick the one that's biggest, right? Or the 2 or the 3 if there's ties. Okay, so I would view that as it's mechanical. It's but it's like, exactly what to do. There's no thinking involved. It's okay, I know what to do. I just apply the formula and do it. So there will be, a number of questions on the final that are of that variety that you don't have to sit there and be like, okay, I haven't seen this game before. Let me think about, like, what's the rationalizable set? What's, like, so I think the final should be easier in the sense that there will be more kind of mechanical plug and chug questions on it. Certainly not all of them, but it'll help build up points. There weren't so many freebies on the midterm as there will be on the final. But the quiz, basically anything that I asked you in the quizzes, anything that I did in the video lectures, the recommended end of chapter questions, like any of that stuff, or deviate, slight deviations from that stuff, that's all kind of fair game to be on the final, and it should be a pretty even spread throughout the semester. But again, like if I asked you a chapter 15 kind of question, that's bringing in multiple chapters, chapter 2, chapter 3, chapter 9, chapter 11, and chapter 15. So like it's, I could ask some of the questions will be multi-part, so.
Thank you.
Yes. Other questions you guys have about, anything? Can we talk about question 8? Question 8, this is Abhishek. Question 8 from chapter 15. Chapter 8 from, let's see. We can start it. Was this on my recommended list? Does anyone remember? It was? Okay. Then we can do it for sure. It looks like it might be a little mathy. This one might go above and beyond the course, but let's at least let's set it up. Number 8. So they simultaneously and independently select A or B. and if they both select A, the game is over. So player one chooses A or B. So again, here's again where like, if I ask you to put this game into the extensive form, you know, this is a chapter 2 question, but it's also a chapter 15 question. A or B, it's a simultaneous move game, so we have to have a dashed line there, and then player two also picks A and B. And if they both pick A, it's over. If they both pick B, it's over, but with worse payoffs. Then the game continues otherwise, and they have to select positive numbers. And then the payoffs here are x1 plus x2 divided by 1 plus x1 plus x2. Okay. And that's for both. All right. And that's a second stage also. So in a sub game, well, let's start with C first. In a subgame perfect Nash equilibria, those choices are going to have to match each other, right? I'm sorry, in a subgame perfect Nash equilibrium, that second stage, conditional on one playing A and one playing B, that second stage is going to have to be played in an equilibrium. So that that X, these choices of X1 and X2 are going to have to be equilibrium choices. Okay. Now let's see. The bottom is always going to be one bigger than the top, and so the top and the bottom are always going to be between, let's see, if they're both 0, it's 0, and as those numbers get large, it goes to 1. And if one player, let's see, what is the best response to a given choice for a given player? What are unfortunately, I think this is I'm trying to think if I'm trying to reason my way through this question to see if I can do it without calculus, because if I use calculus, I'm going to have to use the quotient or the chain rule, and I definitely don't want to require that of the class. So I'm just trying to I'm trying to think if there's a way to reason. So if I take x2 as given, so I take x2 as given, what is my payoff? Is it, so if I pick 0, then I'm going to get x2 over 1 plus x2. And so I should pick the biggest number possible. So I think, let's see, let's make sure I got the payoffs right. Let's see. Yeah, that one's got me puzzling a little bit. So the way my intuition right now is telling me that we want to pick the biggest number possible, because then, and then what is it? each player gets the same payoff. Yeah, I think both players, it seems like that. So the best anyone is going to do is 1, and that's in the limit as these numbers get arbitrarily large. I don't see how you can get a payoff bigger than 1 here. You can't, because whatever you pick, you automatically, even if the other guy does 0, you're picking. Yeah, so I'm not. Even if we took the derivative in this case, I don't think. Well, let's try it. I don't think this is a calculus problem, but let's try it. So we can have the utility to player 1 is equal to, let's rewrite that just so you're probably more familiar with the product rule than quotient rule. And so I take x2 as given as player 1. So let's see, I have 1. Oops, I should tell you what I'm doing here. We have 1, and then 1 plus x1 plus x2 to the minus 1 plus, and then it should just be x1 plus x2 times minus 1, 1 plus x1 plus x2 to the minus 2, and then the inside is just x1, just 1, so that's fine. Okay, so I'm going to have 1 over 1 plus x1 plus x2 plus, I'll make that a minus x1 plus x2 over 1 plus x1 plus x2 squared. Okay, and then this side, now we're going to make it 1 plus x1 plus x2 minus x1 minus x2 over 1 plus x1 plus x2 squared, which is just equal to 1 over 1 plus x1 plus x2 squared. Okay, so that's the best response. Well, that's the derivative. The only way that that represents the best response by setting it equal to 0 is if the second derivative is negative. The second derivative of this, so we're going to get minus 2 times the thing on the inside to the minus 3 times 1. So yeah, that's going to be negative because x has to be greater than 0. So it's going to be 1 over some positive number, and so second. Okay, so that we can set the derivative equal to 0. So 1 over 1 plus x1 plus x2. We want that to equal 0. All right. Let's see. I can take. Yeah, that's the problem. I can't set it equal to 0. There's no way to make this. So yeah, so that it's basically the closest I can get is when both players make the numbers as big as they possibly can. Yeah. So the solution to to the sub game is that both players choose X and X1 and X2 to go to infinity. They want to make those numbers as big as they possibly can. So X1, X2 approach infinity. The key is that in that case, the payoff for both players is just going to be 1, because the limit of those payoffs is 1, and the limit as X1 and X2 go to infinity. Okay, and so in the subgame perfect Nash equilibrium, so now I can write this as, oops, A, B, A, B, A, B, and then this payoff was 5, 5, minus 1, minus 1, and now we know that in the subgame, in the equilibrium of the subgame, X approaches infinity for both players. So payoff approaches 1. So we have essentially this. Okay, and so now you can put that game into the matrix form. A, B, 5, 5, minus 1, minus 1, and 1, 1. And if player 1 chooses A, player 2 picks A, B, so it's a dominant, oops, sorry. If player 1 chooses B, player 1 also chooses, yeah. So dominant strategy. So yeah, the unique SPNE is for player 1 to play A, X is as big as you can picture, and for player 2 to do the same. Oh, sorry, pick A. Okay, so complicated game, especially since there's no solution. Basically, there's no solution that calculus allows us to get to by itself. So we kind of have to reason our way through it. The calculus can show us the direction that the reason should go, and it should be clear that in these payoffs here, because it was X1 plus X2 over 1 plus X1 plus X2, given the choice of the other player, no matter what choice you make, you're never going to get a payoff bigger than 1, right? So if both players pick 0, your payoff is 0, and then this payoff here is increasing in the choice of both players, but it's never going to get bigger than 1. So 1 is the upper bound of payoffs, and 1 is approached in the limit as X1 and X2 both go to infinity. And so if that subgame, that second stage, is played in equilibrium where both players are choosing numbers that are arbitrarily large, then those payoffs are quickly approaching 1 apiece. And so they're both going to choose A off the bat. So it's recognition of what the limits of payoffs could be in that second subgame. Yeah. Yeah. All right. So yeah, definitely that one's above and beyond what we would have to do in the class. Like something, you could get a question on a final that looked like, kind of the same sort of thing. Like here's A, here's a B. If they pick A, there's some payoffs that we know. If they both pick B, there's some payoffs that we know. If they pick here, you go into a second stage game where you pick X and X1 and X2, and then that game has to be played in equilibrium. But I would make this game right here, the continuous game where you're picking X1 and X2, I would make that something that would be calculus solvable. So something, you could have like some kind of effort game, but some kind of game that could be solved, with a unique solution. And then, you plug one best response function into the other best response function, you figure out what your payoffs are here, and then you pick other, and then you decide what to do earlier in the game based on that choice. So the structure of this game is definitely, is a structure that I could put on the final. But this particular game, this idea of kind of thinking about limits of what those payoffs must be, and there's actually not a choice of X1 and choice of X2. Whatever you pick, you should have picked something bigger. So basically, you have to pick infinity, but there is no number infinity. You can only pick numbers that approach, the limit of a sequence of numbers that approach infinity. So that's a little bit too. That's a much too tedious for this class. But the structure of this kind of solution, I hope, makes some sense. That if there's a second stage that gets resolved to determine those payoffs in a subgame perfect Nash equilibrium, figure out what those payoffs are first, plug them in here, and now solve the whole game knowing what you know about how those numbers have to resolve in the subgame. So that idea is nice about this question, but the particular question is trickier than what I would put on the final. All right, questions about that? I know I went fast on the previous page when I was working on the derivations, because I kind of thought the derivations weren't going to get us anywhere anyway. I just wanted to convince myself of it. I hadn't solved this question before, obviously. But questions about that? All right. Other questions from this chapter, other chapters? At this point, we've solved a lot of these questions already from chapter 15, just about all of them. Anyone else have any questions? Did you work through any homework or end of chapter questions that got you stumped trying to figure out what the solutions are?
Can you go over question 14 on the midterm?
Question what?
14.
Question 14. I don't even see a question 14. Which chapter?
The midterm.
Oh, question 14 on the midterm. Sorry.
Right.
Well, I didn't see it. All right, so okay. So we have a 4x2 game. Uh, 12-0. Okay. So the first thing to do, I think, where a lot of people went wrong on this question on the midterm, was that they didn't do iterated dominance first, or in this case, iterated dominance doesn't help, but dominance does, to get rid of strategies. So if you the the biggest mistake that people make on finding mixed strategy equilibria is they start assigning probabilities to all of the strategies before they try to get rid of dominated strategies and iterative dominated strategies. So that's definitely something to keep in mind, that if you're looking for equilibria and they can be pure strategy or mixed strategy, and you haven't gotten things to a 2x2 yet, try the best you can to take it down as small as you can before finding the mixed strategy equilibria, or you're going to create for yourself 10 times more work than is necessary, and the question's going to be a lot harder. And the question's hard enough even if you do that. All right, so if player 1 chooses X, if player 2 chooses X, A is the best response for player 1. And if player 2 plays Y, D is the best response for player 1. So we're definitely not going to be able to dominate A or D. So that's the first thing to recognize, is that A and D are not dominated, and X and Y are not dominated either. Y is the best response to A and B, but D is the best response. X is the best response to D. All right. So X, Y, A, and D are all safe from dominance, and then we look to see can B or C be dominated. Okay. And take your pick as to which one we're going to try to dominate. So I see right off the bat that I can dominate B with a combination of A and C. So B dominated by sigma 1 equal 1/2, 0, 1/2, 0. 1/2. This should be a slightly more weight on the A than the C.
Is it because 12 is bigger than 11 and 4 is greater than 1?
Correct. So
okay.
So basically, if I have A and C, if I put a 50-50 mixture on A and C, that'll give me exactly 11, which is a tie for column X, and it'll give me 2 for column Y. So in column Y, I win, but in column X, it's a tie, which isn't good enough. So now if I put just a tiny, tiny bit more weight on the A and a tiny bit less weight on the C, that number is going to get bigger than 11 by a little bit, and the 2 will shrink, but it won't shrink by enough as long as the epsilon is small enough.
Okay.
I mean, of course, you could do is you could solve it algebraically, and what you'll find is that like you put a probability P on A, put a probability 1 minus P on C, and find out what is the value of P that makes the combination better than B in both columns, and what you'll find is P greater than 1/2. So you would get there the exact same way. But so B is definitely dominated. C is not going to be dominated. So we can just verify that here. If we try to dominate it with a combination of A and B, we would need that 12P plus 9 minus 9P has to be greater than 10. That's the first condition, which gives us 3P has to be greater than 1, P greater than 1/3. And the other column gives us 0P plus 6 minus 6P greater than 4, which means that 6P has to be less than 2. So P less than 1/3. So, but it's not possible to have P be both greater than 1/3 and less than 1/3. So C not dominated. Okay, but getting rid of B was a very important step. All right. Now, so I'm going to look for mixed strategies for player 1 and player 2. I can let the probability that I'm going to mix with for player 1 be R, S, and 1 minus R minus S. You can use whatever numbers you like. In fact, maybe I'll change those to a different color. Just oops. Okay, so we have 3 different strategies, 3 probabilities, and I'll make this a Q and a 1 minus Q on player 2. And so first question I asked myself, this isn't critical who you start with, this is just how I'm going to do it, is what will keep player 1 indifferent between A and C. To keep player 1 indifferent between A and C, we need that 12 times Q plus 0 times 1 minus Q is equal to 10 times Q plus 4 times 1 minus Q. Okay, so if player 1 is going to mix between A and C, he has to be indifferent between A and C, so this must be true. So this puts a restriction on Q. So we need 12Q is equal to 4 plus 6Q. So 4 is equal to 6Q, or Q equals 2/3. Okay, so we know that Q has to equal 2/3 in order for player 1 to be indifferent between A and C. But that doesn't mean that player 1 will mix between A and C, because it's possible that D gives a better payoff than both when Q equals 2/3. And if that was true, then Q equals 2/3 then Q equals 2/3 would not be part of a mixed strategy equilibrium, and player 1 would not be able to play A and C together as part of an equilibrium. Okay, so now we have to see if the utility that returns from A and C is bigger or smaller than D. Okay, so the utility of player 1 of playing A, given that Q equals 2/3, is equal to 12 times 2/3 plus 0 times 1/3, which equals 8. And we know the utility of C must equal 8. That's how we solve for Q in the first place. And the utility for player 1 of playing D, when Q equals 2/3, is equal to 9 times 2/3 plus 6 times 1/3, which is also equal to 8. Okay, so player 1 is indifferent between A, C, and D when Q equals 2/3. And furthermore, if Q is going to be greater than 2/3, that means player 1 is going to like A the most, right? Because it's a 12 and a 0. And so that one's going to ramp up the fastest when Q increases above 2/3. So his best response is A when Q is greater than 2/3. And the best response is going to be D when Q is less than 2/3. And so only 2/3 will have player 1 willing to mix anything. Okay, so Q equals 2/3 is required for player 1 to mix at all. For any other Q, player 1 has a pure strategy best response. And when Q is equal to exactly 2/3, player 1 is indifferent between all 3 of her strategies. And so now we have to consider mixtures potentially of all 3 of those strategies to keep player 2 indifferent from changing between X and Y. Okay, so we know that so first of all, there's no pure strategy equilibrium in this game. And if there's no pure strategy equilibrium, we know there has to be a mixed strategy equilibrium. So we know that in any equilibrium, Q has to equal 2/3. All right, so we've solved for half of our equilibrium. We know that Q is going to equal 2/3. All right, so now we have to find what's going to keep player 2 indifferent. So I'll at least start it on this page. Let's try to carve out a little spot for it. Okay, so to keep player 2 indifferent, we're going to need that 0 times R plus 2 times S plus 3 times 1 minus R minus S has to equal 6 times r plus 2 times s plus 0 times 1 minus r minus s. All right. So we're going to have that 3 minus 3r minus s is equal to 6r plus 2s, which means that 3 is equal to 9r plus 3s, which means that we could say s equals, we can divide everything by 3 and then throw the r on the other side. S equals 1 minus 3r. Okay, so we have a solution that sigma 1 has to equal r 0, because b is never played. 1 minus 3r, that's what we found s to equal. And now this last one is 1 minus r minus s, but we know s is 1 minus 3r, so that's going to be minus 1 plus 3r. And so in that last part, we can simplify. 1 minus 1 is 0. Negative r plus 3r is 2r. Okay, so that's the mixed strategy for player 1. For player 2, we already know sigma 2 is equal to 2/3, 1/3. And the last thing we should do is to put restrictions on r. Like this can't be true for any r. We have to make sure that no probability ever goes below 0 and ever goes above 1. So r is never allowed to be greater than 1/3. So r less than or equal to 1/3. The reason is that if r goes bigger than 1/3, 1 minus 3 times r would be a negative number, and that's not allowed. So that's one restriction. The second restriction is that r has to be less than 1/2, or less than or equal to 1/2. Okay, all right, bye, Ariel. So r has to be less than or equal to 1/2. Otherwise, that last probability could be greater than 1, and that's not allowed. Okay, but of those restrictions, one is subsumed by the other. So r less than or equal to 1/3 is the relevant restriction, because if that's met, then the second restriction is met as well. So that's our mixed strategy equilibria. Is that one for player 2, and this one for player 1, with the restriction that r has to be less than or equal to 1/3. Questions about that?
Got it. Thank you.
All right. I still have it's 10:30, but if anyone has another question or two that they've been waiting to ask, I can still I can still answer a question or two. Does anyone have one? Going once, going twice. We all good?
If I have a question, can I still email you?
Yeah, sure.
Okay.
The closer the email gets to the exam day, the less, you know what I mean? The less likely it is I'll be able, like, sometimes I'll get emails at like 3 o'clock in the morning on Tuesday night. Like
Yeah.
the chances of me being awake at 3 o'clock in the morning on Tuesday night and being sober enough to answer your question is very small. So that's not going to happen. All right, cool. All right, guys. Well, I will see you on Wednesday then. And, you know, happy studying. Stay safe.
Thank you.
Bye, guys.